Okay, in this session, we're going to talk a bit about calculating permutations of groupings that are getting to the point of being too high to count. Now, we'll start with situations that'll be a little bit easier to just think through and count in some cases, but sometimes you'll end up with a situation where the number of outcomes that are possible is just too high to just simply sit out and count. So with these formulas we're going to develop for permutations, we'll figure out some ways to count permutations without having to count each individual possible outcome. So let's get into it. Permutations. Those of you following along at home, this would cover sections 4.3 and 4.5 of your textbook. And we'll start with a description. We've already talked about how if I had 5 different things to arrange, I'll start with 4 different things to arrange. I'll start with 3 different things to arrange. Make life easier. A, B, C. How many ways are there to arrange these? Well, I've got 3 ways to pick the first letter, 2 ways to pick the second, and 1 way to pick the first. By the fundamental counting principle, this should end up being 6. We could more shortly write that as 3 factorial, which equals 6. And I could even show all the different possible permutations here. ABC, ACB, BAC, BCA, CAB, and CBA. 6 different permutations of that group of things. And in fact, n factorial can represent the number of ways number of permutations of n distinct objects. Permutations of n distinct objects. If the objects are indistinct, that becomes a little tricky, and we'll talk about that a bit later in this presentation. So, nice short form, n factorial can represent the number of permutations of n distinct objects. All well and good. Where it starts to get a little more complicated is when you're just trying to arrange subgroups of that. So, for instance, let's say that you've got a security pin on the back of your credit cards that's 3 digits long. So, how many distinct 3-digit security pins can you have if no digit can be repeated? Now, we're obviously talking about permutations here because the order does matter. A security pin of 367 will be different than a security pin of 673. Same 3 digits, but the order makes a difference. If we think about the fundamental counting principle, there are 10 ways to choose the first digit, leaving you with 9 ways to choose the next digit, leaving you with 8 ways to choose the last digit, which is 720. But this doesn't quite so nicely jump out as a factorial statement like the last one did. However, we can still state it as a factorial, because this would be the same as having 10 factorial, but with the 7 down through the 1 canceled out. So it would be 10 factorial divided by 7 factorial. But 10, that was the number of options available. And 7 was the number of unused options. And that lets us write a formula for permutations in general. And we shorten it as NPR. What this represents is the number of permutations my pen is about to die. So we'll switch this up. The number of permutations of a group of size R taken from a group of size N. As a calculation, it would be N factorial over N minus R factorial. And from this example that I had up here, what I'd be looking at is 10 permute 3. The number of permutations of a group of 3 I can take out of 10 digits. That would be 10 factorial over 10 minus 3 factorial, or 10 factorial over 7 factorial, which is 720. You can work this out on your calculator. If you go into math and over to the probability, you'll notice your third option down is an NPR. If you bring that out, it gives you the blank which you can fill your letters or your numbers into. The first number should always be the bigger of the two, since that's the group you're taking elements out of in order to get different permutations. I should also mention that NPR is read N permute R, although I tend to say NPR myself more than anything else. And I also want to stress that this is for distinct objects, objects that are different than one another. That's why we had to have this condition that no digit can be repeated here. If you could repeat digits, then we're not talking about just permutations of the same three things anymore. There'd be 10 ways to choose the first, 10 ways to choose the second, and 10 ways to choose the third, which would just be 1,000, and it would no longer be permutations of the same grouping of three things. An example or two working with this before we start to talk about repeated numbers and repeated objects. First, we've got example 1 off of page 247. Matt has downloaded 10 new songs from an online music store. He wants to create a playlist using 6 of these songs arranged in any order. How many 6-song playlists can be created from his new downloaded songs? So he's got 10 new songs. He wants to pick 6 of them and put them in a specific order. How many ways can he do this? So what you'd end up working out is 10 permute 6, which would be 10 factorial divided by 10 minus 6 factorial, or 10 factorial over 4 factorial. At any point you could use your calculator to work this out. And just to show that again in that base, sometimes it's easier to pull up the last one and work through it. 10p6 would be 151,200. So there are 151,200 different playlists that Matt can create. There's a can underneath that image of me. Sometimes you need to expand upon this a little bit. Example 3 on page 250. We have Tanya, who needs to create a password for a social networking website she registered with. The password can use any digits from 0 to 9, or any letters of the alphabet. The password is case sensitive, so she can use both lower and uppercase letters. A password must be at least 5 characters long, at most 7 characters long, and no characters can be repeated. How many different passwords are possible? So, all digits plus all upper and lowercase letters, that's 10 digits plus 26 letters in the alphabet doubled, 52, 62 characters to choose from. But now you can have 5-character password, 6-character password, or 7-character password. So, first case, a 5-character password. From a group of 62, you want the number of permutations of 5 different things. Using our handy dandy calculator. That's going to be in math, probability, permute, 62p5. Or a lot. And actually, I'm not going to write those out just yet. I'm going to do those all at once. So case 2, 6-character password, which would just be 62p6, and the 7-character password would be 62p7. How many password choices are there in total? The number of ways to choose the 5, plus the number of ways to choose the 6, plus the number of ways to choose the 7. If I work all that out, math, herb, 62p6, plus, and the reason that I put it all in one here is these are going to be large numbers, and I might as well just write one large number down instead of 4. Now, I want to stress there's an e minus 12 on the end of this number. That means e12 on the end of this number. That means times 10 to the 12. So I move this decimal place over 12 digits and have my actual number, which is, let's see, 2 trillion 523 billion 690 million 780,000 different passwords under that scheme. Which seems moderately secure. Now, sometimes there are a few more conditions to hold to. In that particular case, or this particular example, which is example 4 off of page 251, we're dealing with a car lot, a used car lot particularly. 7 different car models are to be parked close to the street for easy viewing. We're told we have 3 red cars and 4 black cars. And told the 3 red, we're given 2 conditions here. The 3 red cars must be parked so there's a red car to each end and the third one in the middle, with the black cars being everywhere else. What does that look like? That looks like red car, black car, black car, red car, black car, black car, red car. And each car is different from each other car. So that means if I hone in on the 3 red cars, there are 3p3 ways to arrange them. If I hone in on the 4 black cars, there are 4p4 ways to arrange them. Now, both of these arrangements have to happen in this situation. For any one situation, you need to have the 3 red cars arranged and the 4 black cars arranged. So what's the overall result going to be? 3p3 times 4p4. In this case, will just be 3 factorial times 4 factorial, or 6 times 24, or 144. 144 different possible arrangements. Now, in the B part of our example, we're told the 3 red cars have to be parked side by side. How can this happen? So I need one block that's got my 3 red cars in it. And my 4 black cars. But that block could happen here, it could happen between these two, it could happen between these two, it could happen between these two. So ultimately what I've got here is 5 objects to arrange, one of which has 3 objects in it to arrange. So arranging 5 objects would be 5p5, or 5 factorial. The arrangement of 3 objects would be 3p3, and again, both of these arrangements have to happen for one total arrangement to be there. So your total is going to be, well, that's the pen that's dying, 5p5 times 3p3. Again, it's going to be 5 factorial times 3 factorial, or 6 times 120, or 720 different possible arrangements. Now we're going to talk a little bit about what happens when you've got identical objects involved. Or do we want to talk about one more thing first? I'll do one more example with this before I get into identical objects. So it does point out an important difference, this example. This is example 5 off page 252. So a social insurance number in Canada consists of a 9-digit number that uses the digits 0 through 9. There are no restrictions on the digits selected for each position of the number. How many social insurance numbers can be created if you can repeat digits? And how does this compare with the situation if you can't repeat digits? So in A, digits can be repeated, therefore this is not a permutation question, at least not a permutation of distinct objects. We fall back on the fundamental counting principle And for a 9-digit PIN number, I have 10 ways to choose the first digit, 10 ways to choose the second, 10 ways to choose the third, the fourth, the fifth, the sixth, the seventh, the eighth, and the ninth. Or 10 to the 9, or about a billion. Insurance numbers. And if you think about it, this should include all of the numbers from 0.000000000 up to 999,999,999, or a billion possibilities. Now, if you can't repeat digits, so if digits aren't repeated, you're then just trying to arrange 9 of the 10 digits between 0 and 9 inclusive, and you end up with permutations again. Digits aren't repeated, order matters, therefore this is a permutation of distinct objects. And we end up with 10p9, which is 10 factorial over 10 9 is 9 factorial. Which is 10 factorial over 1 factorial. Or simply 10 factorial, which works out to 3,628,800. So putting this condition in can actually be quite a limiter on how many objects you can deal with, how many objects you can, or how many outcomes you have to work with. And I just wanted to include that example to show that difference between things that are permutations of distinct objects and things that aren't. Now, to move on and talk about permutations when some objects are identical. Permutations of some identical objects. So, let's say that I have got three black objects, two red objects, and four blue objects that are all now identical to each other. And I'll say that underneath, objects of similar color are identical. How many, I should say, different ways can these objects be arranged? If these objects were all different, there would be 9p9 or 9 factorial ways to arrange them. Different ways to arrange them. And if I think about these 9 things and arranging them in different orders, one of these different arrangements would include, say, switching these two blocks with each other. according to if they were all different. But these two objects are identical to each other, so switching them doesn't really make a different way to arrange it. So in counting the 9 factorial different ways to arrange all these objects, we've ended up double counting some outcomes, double counting some permutations, because they would be identical to each other, because some of the objects are identical. So, how we can take that into account. Take the identical objects into account. So 9 factorial is the total different ways to arrange these 9 objects, some of which are different and some aren't. The black objects, there's 3 factorial different ways to arrange those. So I've overcounted this by a factor of 3 factorial due to the black objects. There'd be 2 factorial different ways to arrange the red objects, and 4 factorial different ways to arrange the blue objects. So in doing these divisions, I am effectively bringing this down to remove all the repetitions of the same grouping of 3 identical objects, and 2 identical objects, and 4 identical objects. You can work that out on your calculator, although you'd probably be able to cancel a lot out if you wrote it out. So numbers are relatively small, and it's good practice. 3 factorial is 3 times 2 times 1, 2 factorial is 2 times 1, and 4 factorial is 4 times 3 times 2 times 1. 4 over 4, 3 over 3, 2 over 2, 1 over 1. 2 times 3 is 6. And 2 goes into 8 4 times. So this would be the same as 9 times 4 times 7 times 5. Or 20 times 63 to 1260. There would be 1260 different ways to arrange these objects. So this is how you deal with permutations when you've got some objects in your group that are identical. You simply divide by the number of ways to arrange the identical objects. And if you've got more than one group of identical objects, you end up with more than one division to account for that. I'll work through a couple of book examples with this. Example 1 on page 262 talks about the mountainous regions of India, China, Nepal, and Bhutan, where it's common to see prayer flags. Each flag has a prayer written on it, and colors used to symbolize different elements: green, yellow, white, blue, and red. How many different arrangements of the same prayer can be made with 1 green flag, 1 yellow flag, 2 white flags, 3 blue flags, and 2 red flags? Well, how many different ways to arrange this? There's 9 flags, so there'd be 9 factorial ways to arrange them. But to take care of the 2 identical white flags, 3 identical blue flags, and 2 identical red flags, I'd have a statement something like this. I want to work that in my head. Do I not want to work that out in my head? I have 9 out of 4. 5, 6, 7, 8, 9, 30, 210. I don't want to do that in my head. 15,120 different arrangements. A couple more examples of this. I have example 2 from page 263. Which I'm going to modify a little bit and break into 2 parts. How many ways and the letters in the word Canada be rearranged? Well, there's 7 letters, so there'd be 7 factorial ways to arrange those. But the A repeats itself 3 times. Nothing else repeats. So you'd have 7 factorial divided by 3 factorial, or 7 times 6 times 5 times 4. 4 times 5 is 20, times 6 is 120, times 7 is 840. Now how many ways to arrange them if the first letter must be N and the last? So what that does is it fixes the N and the C in place, and then you've got 5 more letters to arrange there. So what I have just realized is there are not, in fact, 7 letters in the word Canada, which I've correctly spelled up here, but 6. So kudos to me for my counting ability in this counting section of math. This would become 6 factorial over 3, or 6 times 5 times 4, which would be 120. So in this case, the N and the C are fixed on the ends, and I've got 4 letters to rearrange in the middle in any sort of way. So we only concern ourselves with the arrangement of the AAAD in the center, as there is only one way to arrange the N and the C. So I've got these 4 things to rearrange, 3 of which are identical, which is just going to work out to 4. Are 4 possible arrangements. Now example 3, we'll do that on a separate page because I'll talk about it a little bit, and the grid is helpful for it. Example 3 on page 264. It's a fairly common problem that crops up in math by times, and it's grid counting. We've got Julie's home is 3 blocks north and 5 blocks west of her school. How many routes can Julie take from home to school? She always travels either south or east. I'll try to make myself a fairly good sized grid here. Home. Here is school. And Julie can either travel east or south with each step. Now, you can try just starting to count routes. Here's one route along here, one route along here, and so on. That quickly descends into madness, so I wouldn't recommend going that way. There are really 2 kinds of ways you can work through this. The one is to sort of count possibilities to each point. If I start out home, there's only one way I can travel to this point. There's only one way I can travel to this point, one way I can travel to this point, one way I can travel to this point, one way I can travel to this point. There's only one way I can travel to this point, but now here, to this point, I've got one way to travel and another way to travel, so there's two ways. From here, since there were two ways to get to here and one way to get to here, there's three ways to get to this point. Here, since there's three ways to get here and one way to get here, four ways to that point. Here, four ways to this point, one way to this point, so five, and similarly, six ways to get to that point. There's only one way to get to here, but 1 and 2 makes 3 ways to get here. 3 and 3 makes 6 ways to get here. 6 and 4 is 10 ways to get to this point. 10 and 5 is 15 ways to get to this point. And 15 and 6 is 21 ways to get to this point. We're almost there. One way to get down to this corner. 1 and 3 is 4 ways to this point. 4 and 6 is 10 ways to this point. And then 10 is 20 ways to this point. 20 and 15 is 35 ways to this point. And finally, 35 and 21 is 56 ways to get to school. Now, there is an easier way to do this. In order to get from home to school, Julie's going to have to travel at some point along the way 5 blocks east and 3 blocks south. So that's 5 blocks east, 3 blocks south, and any order that she travels this in will be a different route, or any different order that she travels this in will be a different route for getting from home to school. So this is pretty similar to us rearranging letters in Word. There's 8 factorial ways to rearrange these, but 5 factorial of them are ways to arrange the E's. 3 factorial of those are different ways to arrange the S's, and I end up with 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1 times 3 times 2 times 1. 5, 5, 4, 4, 3, 3, 2, 2, and then the 3 and the 2 and the 6, and I have 8 times 7, or 56, which is again another way to show the 56 different paths to school. Alright, I'm going to leave it at that for now. Again, that was sections 4.3 and 4.4. There will be some practice questions to go along with this in the Google Classroom. Thanks for watching.